Hey everyone, welcome back. Today we're diving deep into a really cool area of AI research. It's called RLHF. It stands for Reinforcement Learning from Human Feedback. And we like to tailor these deep dives to you, the listener. So if you're a software engineer, a software architect, or even a CTO, this one's for you. We're going to unpack this whole RLHF process in a way that makes sense for software folks, using code examples and drawing parallels to concepts that we're already familiar with in the world of software.
Sounds exciting.
And our guide for this journey is going to be Nathan Lambert's RLHF book, which is a fantastic resource that really digs into the nitty-gritty of RLHF, for the algorithms to the practical considerations.
It's incredible how this field is evolving so rapidly. I mean, just a couple of years ago, RLHF was this niche research topic, and now it's driving some of the most powerful language models out there.
Yeah, it's mind-blowing, and it really highlights the power of human feedback. In shaping how AI systems learn, think about it, we're essentially teaching these models to not just generate text or code, but to generate text and code that aligns with what we humans consider to be high quality.
It's like we're instilling a sense of good taste in these AI systems.
Totally, like teaching them to appreciate not just functional code, but elegant code, maintainable code, code that would make a senior developer nod in approval.
Yeah, exactly. It's almost like we're giving these language models a crash course in software craftsmanship.
Now, to really appreciate the power of RLHF, I think it helps to step back and understand the basic flow of how this whole process works.
Okay, so let's say we want to train a language model using this RLHF magic. It all starts with a pipeline, a series of steps that we carefully orchestrate.
Right, so think of it like a software development pipeline. We've got different stages, each with its own purpose.
Exactly. So the first stage is where we start with our base language model. Think of this as our fresh out of boot camp junior developer. They've got the basic coding skills, but they still need a lot of guidance to really excel.
Got it. So we've got our eager but inexperienced coder ready to learn. What's next?
Now comes the human element, the secret sauce of RLHF. We need to gather preference data. And what that means is we need to get feedback from experienced developers on which code completions are better for a given coding task. It's like giving our junior dev a coding challenge and then having senior engineers review their solutions, ranking them from best to worst.
So it's like crowdsourcing code reviews at a massive scale.
Yeah.
Tapping into the collective wisdom of seasoned developers.
Exactly. And this data is pure gold because it captures those subtle human insights about what makes code truly great.
So we're not just looking at whether the code compiles or passes tests. We're looking at the elegance, the efficiency, the readability, all those things that experienced developers value.
Now, once we have this precious preference data, we use it to train a reward model. And the reward model is like giving our junior developer a special tool that can analyze their code and tell them how closely it aligns with what the senior engineers prefer.
Okay, so this reward model is starting to sound like a super-powered code reviewer.
That's a great way to put it. It's like having a virtual mentor that can give our language model instant feedback on its coding style.
So we've got our base language model,
Yeah.
our human feedback in the form of preference data, and our reward model, which acts like a sophisticated code quality analyzer. But how do we actually use this reward model to improve our language model's coding skills? How do we bring these pieces together?
That's where the reinforcement learning magic comes in. We employ techniques like PPO, which stands for Proximal Policy Optimization. It's a mouthful, I know.
No worries. Acronyms are our bread and butter in the software world.
And we use PPO to essentially use the reward model as a guide for our language model. Every time the language model generates some code, the reward model gives it a score based on those human preferences. Over time, the language model learns to generate code that gets higher and higher scores.
So it's like we're giving our language model constant feedback,
Yeah.
nudging it towards writing code that would make senior devs proud.
Exactly. And Lambert's book dives deep into this whole process of training the reward model and optimizing the language model.
Yeah.
Using techniques like PPO, he calls this preference fine-tuning.
Preference fine-tuning.
Yeah.
I like it. It has a nice ring to it. But before we get into those specifics, I think it's worth pausing for a moment to consider something pretty fundamental. How do we even capture something as complex and nuanced
Yes.
as human preferences in a way that we can feed into an AI system? It's not like we could just plug in a USB cable and download those preferences.
You've hit on a really important point. It's surprisingly tricky to capture those subtle human judgments about code quality. I mean, it's not just about finding bugs. It's about understanding things like elegance, efficiency, maintainability,
Yeah.
those harder to define qualities that make code truly great.
Right, it's like we're trying to translate the art of coding into the language of mathematics.
And that means we have to be really careful about the assumptions we're making when we collect this preference data. Just because we can gather feedback and train a model doesn't mean we've perfectly captured what makes code truly good, or that our reward model is completely aligned with human values. There's a lot of ongoing research in this area.
It's a reminder that even with Apolpis, all the advancements in AI, we still need to be mindful of the human element
Yeah.
and the limitations of our data and our models. But hey, that's what makes this field so fascinating, right? It's not just about writing code. It's about understanding human nature.
Absolutely. And that brings us to an interesting question. How do we as software engineers make sense of this whole RLHF process? I mean, it seems so different from traditional software development.
Yeah, it's a bit of a mind shift for sure. But I think there's a way to frame RLHF that makes it click for software folks. We just need to think about it as a modified version of classic reinforcement learning, the kind of RL that we might already be familiar with from other AI applications.
Oh, okay. I like where you're going with this.
So in a typical RL setup, you've got an agent interacting with an environment, taking actions, getting feedback in the form of rewards, and learning to maximize those rewards. It's all about trial and error, learning from experience.
It's like a video game where the agent is trying to rack up the highest score.
Now in RLHF, things are a bit different. Instead of interacting with a traditional environment, our agent, the language model, is interacting with that reward model we talked about. The prompts are like the initial state. The code completions are the agent's actions. And the reward comes from the reward model, which tells us how much humans would like that particular code.
So the reward model is like a virtual coding mentor, constantly evaluating the language model's work and giving it feedback.
Exactly. And unlike typical RL, there aren't any state transitions in the traditional sense. We give a prompt, the model generates a completion, and we get a reward based on that completion.
It's kind of like a bandit's problem in RL.
A bandit's problem. Can you unpack that a bit?
Sure. Imagine you walk into a casino with a row of slot machines, each with a different payout probability. Your goal is to figure out which machine gives you the biggest wins on average. That's essentially a bandit's problem, choosing the best action to maximize your rewards.
Okay, I see the analogy. So in RLHF, we're treating each code completion like a pull of the slot machine lever.
Right.
And the reward model is telling us which completions are more likely to hit the jackpot of human approval.
That's a great way to visualize it. And to make this even more concrete, we can even look at the RLHF objective function. You know, that mathematical equation that captures the goal of the whole RLHF process. It really highlights that bandit-like nature.
All right, let's see it. I'm ready to get a little mathematical.
Okay, so here's a simplified version.
Uh-oh, math.
It's not as scary as it looks.
Okay, good.
So it's ger arrest at, now let's break this down. Ger represents the performance of the language model's policy, which we denote by...
So O is like our strategy for generating code.
Right. And the ito part means we're looking at the expected reward when the language model follows its policy. Rest at is the reward given by our reward model res for the current prompt S and the code completion at.
Okay, so it's saying that we want to find the policy for our language model that's going to give us the highest expected reward based on the preferences captured by that reward model.
Exactly. You got it. And you can see the similarity to the objective function. For a bandit's problem, we're not concerned with complex state transitions. We're focused on maximizing the reward for each individual code completion, just like we're trying to maximize our winnings on each pull of the slot machine.
So we're all about finding those code completions, those winning slot machine pulls that are most likely to get a thumbs up from our human reviewers.
Now that we've laid this foundation, let's dive into the core building blocks of this RLHF pipeline, starting with the collection of that all-important preference data. After all, as we software folks know, garbage in, garbage out. The quality of our data is critical for building a robust system.
Absolutely. The quality of our preference data is everything. It's the fuel that powers our entire RLHF engine. So let's get down to brass tacks. How do we collect this data? Do we have an army of developers sitting around reviewing code 247 #TTS? The Deep Dive episode 2025-02-01, part 2 of 3.
Well, while having a dedicated army of code reviewers sounds amazing, it's not quite how it works in the real world. I mean, there are a couple of main approaches to gathering this kind of data. One option is to work with specialized vendors who handle data annotation. You know they have trained teams who can follow detailed instructions and give consistent, high-quality feedback on code, which can be a huge help, especially if you're just starting out with RLHF.
So it's like outsourcing a critical part of your development process, tapping into expertise that you might not have in-house, but I imagine there are trade-offs, right? I mean, it's never as simple as just throwing money at a problem.
Definitely. Just like with any outsourcing, you need to do your due diligence, make sure you choose a vendor with a solid reputation, hammer out clear contracts, and have robust ways too. Check the quality of the data you're getting. It's always a good idea to run a pilot project before committing to a larger scale effort.
Makes sense. Got to make sure we're getting our money's worth. Are there any other things to keep in mind when working with vendors, like any gotchas or pitfalls?
One of the biggest things is having crystal clear instructions for your annotation tasks. Remember, we're dealing with something inherently subjective here, human opinions about code. You need to be super specific about what you want, providing examples of good and bad code, defining your evaluation criteria, and specifying the exact format you need the data in.
It sounds like writing these instructions is almost like designing a whole new piece of software with its own set of tags, requirements, and edge cases. It's not just a quick write-up.
It's more involved than you might think. And don't be surprised if you need to. Tweak those instructions along the way based on the feedback you get from the annotators and the quality of
The initial data.
It's an iterative process, just like any other development cycle.
You're constantly refining the instructions, almost like debugging your data collection process.
Yeah, and, once you've got your
Smoker Anderson Vale.
yeah, your instructions nailed down, you need to be prepared for the actual data collection process. It can be time sensitive, especially if you're working with more complex coding tasks that need specialized knowledge.
Right, you can't expect to have a perfectly labeled data set ready to go overnight.
Vendors often manage their workforce, like we manage. Compute resources, carefully allocating people to different projects. Based on availability and skill set, you might need to book time slots weeks in advance, especially for areas like mathematical reasoning or advanced code generation, where you need annotators with serious technical chops.
So it's like reserving time on a high-performance computing cluster. You got to plan ahead.
Exactly. And once the data starts flowing in, you need to have your infrastructure and analysis tools ready to roll. You've got to be able to quickly check the data quality, spot any potential problems, and make decisions on the fly about how to proceed with the RLHF process.
So it's like managing a live production system. You're constantly monitoring, tweaking, and responding to changes in real time.
Yep, spot on. And speaking of constant tweaking, that brings us to another important aspect of data collection for RLHF. It's iterative. You might start with a set of instructions, gather some initial data, and realize you need to make changes based on what you're seeing. That means working closely with the vendor, refining the instructions, and maybe even recollecting some of the data.
So it's a back and forth process, like code reviews themselves,
Yeah.
where you're constantly striving for better quality and alignment.
Right, and that iterative approach can eat up time and money. You might end up spending a good chunk of your budget on data that doesn't even make it into the final model. It's just part of the cost of doing RLHF right now.
Sounds like there are a lot of moving parts to manage. So even though working with vendors can streamline things, there's still a lot of hands-on work involved in getting this preference data right.
Absolutely. Now, on the flip side, you could also consider building your own in-house annotation team.
That sounds like a major undertaking. What are the pros and cons, though, going down that path?
It definitely requires more upfront investment. You need to recruit and train annotators, build out your own annotation platform, and figure out your own quality control systems. But the upside is that you get way more control over the data, which can be crucial if you have very specific requirements, or if data privacy is a top priority.
So it's a classic build versus buy decision with all the usual factors to consider: costs, benefits, risks.
Exactly. Now, whether you go with a vendor or build your own team, the process of collecting this preference data for RLHF can feel very different from traditional software development. We're not just defining clear-cut rules and logic we're trying to capture. These inherently subjective human judgments about code quality, which can be messy and unpredictable.
It's like we're venturing into the realm of human intuition, trying to understand what makes code good in a way that goes beyond just the way it compiles or passes unit tests.
Exactly. And that means we need to be comfortable with ambiguity and iteration. Things might not go as planned. We'll need to adjust our approach, and we'll definitely learn from our mistakes along the way. It's a journey of discovery, just like any other software development project, but with its own unique set of challenges and rewards.
Speaking of rewards, let's shift our focus to that key component of the RLHF pipeline, the reward model itself. We've talked about gathering all this preference data, but now we need to figure out how to actually use it to train a model that can guide our language model's learning.
This is where we start to bridge the gap between those human intuitions about code and the mathematical world of reinforcement learning. The reward model is really the heart of RLHF. It's what allows us to turn those subjective human judgments into something that an AI system can actually understand and learn from. Hashtag TTS, the Deep Dive episode 2025 U201, part 3 of 3.
Okay, so we've painstakingly gathered and labeled all this preference data about what makes for good code. Now it's time to build that reward model, that AI-powered code reviewer that's going to guide our language model toward producing truly awesome code.
Exactly. The reward model takes center stage now. It's a fascinating adaptation of a classic reinforcement learning concept in a traditional RL setup. You've got an agent learning by interacting directly with an environment, but in RLHF, our language model's environment is this reward model, which we've carefully trained to reflect those human preferences we collected.
So it's like we've built a custom training ground for our language model, a virtual coding dojo where it can spar with this reward model and learn from its feedback.
And one of the most popular tools for building these reward models is the Bradley-Terry model, which we touched on earlier. It's really good at analyzing rankings and preferences, and in the world of RLHF, it helps us translate those human judgments about code into a mathematical framework that our model can understand.
I'm curious to see how this actually works in practice. How do we go from those pairwise comparisons of code to a fully fledged reward model?
Well, the first step is to take our language model and give it a slight makeover. Instead of having it churn out lines of code, we want it to generate a single score, a number that reflects how much a human would like a particular piece of code. Think of it like a movie rating system, but for code.
So we're turning our language model into a code critic, a virtual judge for the coding competition.
And to do this, we can add a simple linear layer on top of our language model's existing architecture. This layer takes the language model's internal representation of the code, those complex vectors that capture the meaning of the code, and squashes it down into a single numerical score.
So it's like we're asking our language model on a scale of 1 to 10, how good is this code?
Now, to train this modified language model, our reward model, we feed it that delicious preference data we've been working so hard to collect. Remember those pairwise comparisons where human annotators told us which code completion they preferred? We use those comparisons to teach our reward model to distinguish between good and bad code.
So it's like showing a student examples of good and bad writing and helping them develop their own sense of what makes writing effective.
Exactly. And to do this effectively, we need to define a loss function. This is a mathematical expression that tells us how well our reward model is doing during training. We want the reward model to give high scores to code humans liked and low scores to code they didn't like.
So the loss functions is like a measure of how aligned our reward model is with those human preferences. The lower the loss, the better our model is at capturing what humans like.
Precisely. And a commonly used loss function for this kind of task is based on, you guessed it, the Bradley-Terry model. It looks a bit intimidating at first, but it's actually pretty straightforward.
Hit me with it. I'm ready to see the math.
All right, so here it is. Don't worry, it's not too bad. It's LXLL. Now let's break this down. L is the loss, which we want to minimize during training, represents the parameters of our reward model, all those internal settings that determine its behavior. X is the input prompt, YW is the code completion that humans preferred the winner, and L is the code completion they didn't prefer the loser row, is our reward model, and L is the sigmoid function, which squishes the output of our reward model between 0 and 1, turning it into a probability.
So we're basically comparing the scores assigned to the winner and loser code snippets and trying to push those scores further apart during training.
That's the gist of it. We want our reward model to be confident in its judgments, giving a clear thumbs up to good code and a thumbs down to code that needs improvement. And as we train the model, we're constantly tweaking those parameters to make its predictions match those human preferences as closely as possible.
So it's an iterative process of refinement like any machine learning model we feed it. Data adjusts its parameters and repeat until we're happy with its performance.
Now, the cool thing is that implementing this reward model, loss in code, is pretty straightforward, especially with libraries like PyTorch. Here's a quick example.
Awesome. Let's see it.
Okay, so in Python, it will look like this. Import torch.nn as NN, rewards chosen, model input chosen, rewards rejected, model inputs rejected, and finally the loss. Loss-nn.functional.log sigmoid, rewards chosen, rewards rejected.
Wow, that's surprisingly concise. It seems like a lot of the heavy lifting is happening behind the scenes within the model itself.
That's the beauty of modern machine learning tools. They abstract away a lot of the complexity, letting us focus on the higher level concepts.
Now, you mentioned earlier that there are other ways to build reward models. What are some of the alternatives to this Bradley Terry approach?
Well, one option is to skip the dedicated classification head and just use a linear layer directly from the final embeddings of our language model. This is a bit simpler, but it might not capture as much detail about what makes for good code.
So it's a trade-off between simplicity and the level of nuance the model can capture.
Right. And there are other variations like the preference margin loss, which takes into account not just which code snippet is better, but also how much better it is if one piece of code is significantly better than another. This loss function reflects that stronger preference.
So we're getting even more precise in how we translate those human judgments into something the model can learn from.
And for cases where you have multiple annotators ranking a bunch of code snippets, you can use the kwise loss function. It allows you to factor in all those rankings, giving you a more robust reward model that captures a wider range of perspectives.
It sounds like there's a whole toolbox of techniques we can use to build these reward models depending on the type of preference data we have and the level of granularity we need.
Absolutely. RLHF is a rapidly evolving field with researchers constantly exploring new ways to build and train these reward models. But the fundamental idea remains the same. We're trying to bridge the gap between human intuition and AI by teaching our models to recognize and value the qualities that make for truly great code.
It's an exciting time to be a software engineer with all these powerful AI tools emerging. I can't wait to see how RLHF and other techniques shape the future of how we build software.
Me too. It's a testament to how human ingenuity and creativity can push the boundaries of what AI can achieve.
Thanks for joining us on this deep dive into RLHF. I hope you've enjoyed this journey through the world of human feedback reward models and the quest to build AI systems that can truly understand and generate amazing code.
It's been a pleasure. Keep experimenting, keep learning, and keep pushing the boundaries of what's possible with AI and code.
Until next time, happy coding, everyone.